we are going to discuss the variance of geometric random variable with parameter p. Suppose that x is such a random variable. Then the variance of x is equal to 1 minus p divided by p squared. And then this number, it turns out that it is less than or equal to 1 over p squared. So let's try to prove why the variance is equal to the number as we claimed. So we are going to use two different proofs for this one. The first proof is from definition. So again, we are going to compute expected of x squared first, and later deduct from it the square of expected of x. So by definition, expected of x squared is equal to the weighted sum of the values of j squared, and the weight is by the chance that x is equal to j, and x is equal to j with this occurrence chance, p times 1 minus p to the power j minus 1. And then this j squared, we are going to separate it into two parts. The first one is j times j minus 1, and the other part is j. The purpose of doing so is because we want to get a simpler formula to compute the values. So first of all, let us focus on the orange part. So for the orange part, we intentionally want to make j times j minus 1 multiplied by 1 minus p to the power j minus 2. We want to get something like this, of this form. So in that sense, we take out one copy of p and one copy of 1 minus p outside. So we get it, this is the same as the orange part. And for the blue part, we hope to get something like j times 1 minus p to the power j minus 1. So in order to get this one, so we need to get away a copy of p outside. So we get this as a result. Now, why we want to have something like this? It is because we can make use of the formula on infinite sums that we have explained earlier in lecture 5. So here is something like this. So recall that we have formulas for something like 1 plus 2r plus 3r squared plus 4r cubed and so on and so forth. And then if you compare this with the blue part, so it is like j, and then this is j minus 1. So let's look at this one again. So it is this formula. So this is j, and the power is j minus 1. j, and the power is j minus 1. So actually, the blue part here can be simplified by using the formula that we have studied before. And now for this one, this is again easy. By differentiating this one with respect to r one more time, we will get the formula for the summation of this term. So in that case, this one can also be simplified. So I will leave this as a homework for you to find out what is the term. But if you look at the next slide, then you will see, okay, so the orange part, we have taken out p times 1 minus p outside. And for the summation part, we can say that, or we claim that it is equal to 2 divided by p cubed. And similarly, for the blue part, we have already taken away p outside. And for the remaining summation, it is evaluated to be 1 over p squared. So after simplifications here, we get this one is equal to 2 minus p divided by p squared. Now to get the variance of x, then we are going to deduct from this term 2 minus p divided by p squared by the square of the expected of x. But for geometric random variable, the expected value is easy. It is just 1 over p. So we are going to deduct 1 over p squared from it. So there is 2 divided by p squared and then minus 1 divided by p squared. So we get 1 minus p instead of 2 minus p here. And then finally divided by p squared. So this is the end of the first proof. Now we are going to proceed for the second proof. So the second proof is by using conditional expectation formula. And again, we are going to compute expected value of x squared. So if we can get the same result as before, if we can get expected of x squared to be the same as like 2 minus p divided by p squared, then we are done. because after that we are minusing the same thing to get the variance of x. So here we focus just on finding expected of x squared. Now by conditional expectation formula, let us divide the whole sample space into two different cases that are disjoint. The first one is the first flip or the first trial is successful. So I'm saying first succeeds to represent this case, and the other case will be the first trial fails. So expected of x squared can be written as the weighted sum of expected of x squared given the first case plus expected of x squared given the second case. The corresponding weight will be the probability of whether the first trial is successful or whether the first trial is failing. Now, let us try to simplify this formula and examine each term one by one to do the simplification. So first of all, given that the first trial succeeds, then the total number of flips is always equal to 1. So that means that x is 1 unconditionally, always 1. So x squared is always 1. So the expected value of this one is 1. And then the probability of the first flip or the first trial is successful is p. And then this one we don't know yet, but then we will simplify this later. So we keep it here. And then this one, the probability that the first one fails is 1 minus p. So we get the second equality here, this line. And then x squared, given the first trial fails, we are going to express this x as 1 plus z, where 1 counts for the first trial and z counts for the remaining trials, so the number of trials after the first trial. So we can replace this x by 1 plus z. Okay, so let's see the effect. Now notice that after the definition, okay, or under the condition that the first flip, the first trial fails, then the number of remaining trials that we need is actually a geometric random variable with parameter p. So in that case, under this condition, first fails, the z here is the same as a geometric random variable with parameter p. So I'm replacing this one. So this time you don't need to have the condition, because the condition that z fails is equal to geometric random variable. So we can just replace that by geometric random variable with parameter p here. But x itself is also a geometric random variable with parameter p. So whether we talk this one and whether we talk about x is the same. So I can now replace this as x. And so the next line, we will do a lot of simplifications. So 1 times p, we get p here. And expected of 1 plus x squared, this number, this is equal to 1 plus expected of x squared plus 2 times expected of x. This is by linearity of expectation. And then this term is multiplied by 1 minus p. Okay, so now let us further simplify this formula or this equation a little bit. So we are going to use eyeball to do the simplification. So on the left-hand side, we have expected of x squared, and on the right-hand side, we have 1 minus p copies of expected of x squared. So the net difference will be p times expected of x squared. So we can now cancel this x squared, expected x squared, by moving it to the left-hand side. So it is p times expected of x squared left. Now we have this term p. We have a term 1 times 1 minus p, so that we have p plus 1 minus p, so it is equal to 1. And finally, this is a term that we have not handled yet. So this is simply 2 times 1 minus p times the expected value of x. Now the expected value of x is 1 over p, so we get this one divided by p. Okay, now let us focus on the right-hand side. So the right-hand side is 1 plus 2 times 1 minus p divided by p. So this one, you can think of this as p divided by p. So we have p divided by p plus 2 minus 2p divided by p. So after doing some cancellation, we will see that this is equal to 2 minus p divided by p. And finally, we move this p to the right hand side, so we get the same conclusion that expected of x squared will be equal to 2 minus p divided by p squared. Since we get the same expected value of x squared, we will get the same value for the variance of x. So this is the end of the second proof.